We're going to start with series and parallel. Deal with how we deal with, Kirchhoff's rules in these situations. And then we'll talk about stepwise reduction. And if we have the time, we'll talk about situations in which stepwise reduction doesn't work. Because although series and parallel is nice, there are quite a few circuits that don't actually fit the bill of either series or parallel. They are actually more complicated than that. So let's start with a basic set of series resistors. So again, there are two rules that we're trying to utilize here to kind of analyze the circuit. Kirchhoff's first rule deals with voltage and voltage drops. The second one deals with current. So a single loop like this, once the switch is connected, the current everywhere in the loop has to be the same at all points in the loop. And that occurs instantaneously after the circuit is connected. So no matter where we look at this loop, the current will have to be the same at all points in the loop. Now, there are three resistors in this loop and a power supply. So if we consider one continuous loop through the circuit, like so, the sum of the voltage drops would have to equal 0 in this continuous loop. So I have the voltage from the circuit that's being added to the circuit due to the potential difference that's applied. It's positive because I chose my loop to be in the direction of the small plate to the big plate, the direction of increasing potential across my potential difference. But then there'll be a voltage drop across resistor 1. There'll be a voltage drop across resistor 2, and there'll be a voltage drop across resistor 3. Now, remember, our goal here is to try and compare this circuit to an equivalent resistance that the battery sees. The battery doesn't know that there are three resistors connected to it. It knows that there is a total resistance that is connected between its plates. It is providing a potential, and therefore there is a total current being provided to the circuit. It doesn't know if there's one resistor or 100 resistors. It just supplies current to the circuit based on the resistance load that's between the plates. Now this sum of voltage drops has to equal 0. And we're going to do the same thing here that we did when we had a capacitance circuit. We're going to try and express the voltages in terms of the way or manner in which these objects utilize the potential. For a capacitor circuit, you'll recall we said that voltage across a capacitor was related to the charge and the potential of the capacitor. For resistors, voltage across a resistor is based on the current that passes through the resistor and the size of the resistor. So for us, we can say that this can be simplified to look like this. I'm not sure if simplified is the right word. But this also does suggest, if I take these all over to the other side, and divide both sides by the current, now consider this, V over I. I could substitute an R in here for the V divided by I. And when I do, what I'm actually replacing here is R equivalent. If you have resistors in series, the equivalent resistance is just the simple sum, because that's what the battery thinks has been applied. more than one way. I've got to do this for resistors in series, and then I should repeat this for resistors in parallel. So we can see how the parallel system works. But I think you already know what's going to happen if the series capacitors is inverses and the parallel capacitors are simple sum. And the first thing I show you for resistors in series is that they are the simple sum. You might get in your head that maybe resistors do the opposite when they're in parallel. But I like to prove. Let's try and prove that with a simple parallel circuit. So R1, R2, R3, and there's our capacitance. Now, the problem here, of course, is that there's a lot of potential loops here to analyze the circuit. You guys see that, right? Now, when trying to solve a circuit and you're wondering, well, which loops should I use? Not all loops are going to be as useful to you as others. For example, when I look at this, I see, let's see, this loop. I see this loop, this loop, this loop, and that loop, and maybe this loop. So 6 different loops, each one a potential way of solving the circuit. Which one should I use? There's an answer to that. If you want to solve your circuit, you need to choose enough loops so that you take in each circuit element. So I don't need all of those because some of those are repetitive. They take in a circuit element that's already been taken in by a different loop. But you do have to have enough of them so that you take in every circuit element. So I tend to find working with the potential difference to be the easiest way to go. So I try to work it in when I can. So I think that the red loop, fine. I think the green loop is a good idea. I think the yellow loop is a good idea. Those are going to be the loops that I'm going to use. Now, there are some problems here, and I hope you kind of anticipate some of these problems. First, I have V minus V1 equals 0, V minus V2 equals 0, and V minus V3 equals 0. You guys follow all that okay? Well, I'm also noticing that there's several junctions here, places where the current separates. Now, I'm afraid that this drawing is misleading as to what's happening with the current and might be confusing to you guys. So I want you to understand that although we tend to draw circuits like the one up above, this circuit might help you understand the current a little bit better. Because it might not look that way in the top circuit, but this bottom circuit is actually what's happening. That there is a certain amount of current that is leaving the battery and approaching this junction. And based on Kirchhoff's second rule, there is a current that goes here. I'll call this I1. And a current that goes here, I'll call this I2. And a current that goes here, I'll call that I3. And that there is a total current that enters that junction and 3 currents that exit that junction based on Kirchhoff's Second law, the current into a junction has to equal the current out of a junction. So I total has to equal I1 plus I2 plus I3. That okay so far? Well, if I go back over here, so what I'm trying to do here, of course, is find a way of relating the resistances. That's really our goal here. So although we have a whole bunch of information about the circuit, I want to try and relate the resistances. So I want to work in resistance where I can, like right here. This V has to equal R1 times V1. I'm sorry, R1 times I1. Right? The voltage across resistor 1 is IR. Just like the voltage across resistor 2 has got to be IR as well. Just like the voltage across resistor 3 has to be IR as well. Now I'm noticing that I have this sum right here. I could work in all of the resistances by just substituting over there, which is exactly what I'm going to do. I'm going to put that this is equal to, I'll take each one of these, I1 equals V divided by R1. So this is going to be V divided by R1 plus V divided by R2 plus V divided by R3. On the other hand, I hope you remember that the battery supplies current to the circuit based on the total equivalent resistance placed between its terminals. So this has got to be V over R equivalent for the battery. I can replace the total current, this, with what the battery thinks has been placed across its terminals. Of course, all the V's can be factored out and removed, which gives me a relationship for the equivalent resistance for resistors in parallel. And it is just the sum of the inverses. So, Kirchhoff's rules can give us a manner of solving a circuit based on the resistors in parallel or resistors in series. And I hope now you see that basically it's the same thing as capacitors, just reversed. So memorization, keep them memorized. Although whenever we have a circuit that has both resistors and capacitors in it, we tend to not have to do this very much because capacitors and resistors do different things. So we will have RC circuits, which have resistors and capacitors in them. But for the next couple of days, we're going to deal with just resistor circuits. And so let's talk about stepwise reduction versus Kirchhoff's laws for just a minute. It's hard to use Kirchhoff's laws with capacitor circuits because there really isn't any current. And so the current rule doesn't work particularly well with capacitor circuits. But with resistor circuits, they do. So I never did this complex capacitor circuits. We only did stepwise reduction. But I want to at least demonstrate to you why Kirchhoff's laws can be used to solve any circuit. And then we'll talk about stepwise reduction. Kirchhoff's rules is like Newton's laws in that it is the absolute hardest way to solve any circuit. It will solve any circuit. Any circuit can be solved, meaning any circuit's ability to do something can be predicted by using Kirchhoff's laws. The problem is that Kirchhoff's laws represent the absolute hardest way to deal with the circuit. So we will find other ways. It's funny because so this is R1, R2, and R3 and R4. Right now in this circuit, there would have to be V1, V2, V3, V4. And based on Kirchhoff's second law, there'd have to be I1, I2, and I3, 4. They would have to have the same current, right? You guys see why that has to be true? They're in a line. There's no break. Okay. So my first equation is going to be that I1 has to equal I2 plus I3, 4. That has to be true. If I pick this loop, and that's my voltage supply, then V equals V1, V1 plus V2. Some of the voltage drops equals 0. I'm just moving it around to the other side. There's also this loop, though, where V has to equal V1 plus V3 plus V4. There's also this loop in here where negative V2 minus V3 minus V4 has to equal 0. They're all voltage drops because not one of them is adds potential. And then for every resistor, there's V1 equals R1 I1, V2 equals R2 I2. Yeah.
For the minus V2, V3, so they're all negative. So how does that equal like V1 minus V2?
I understand what you're saying. You don't have to convince me. But one of them must have an increase in potential, and the other one of them must have a decrease in potential. We just don't know which is which. Only batteries can we guarantee are an increase in potential because they are coded that way. Now, I'll tell you, we're missing something, and that's something I can put in here yet, which is why I'm being evasive on purpose. But in our loop, if we are going against the direction of the current, then that particular resistor must have an increase in potential, meaning we would list the current as being negative compared to our direction through the circuit. And I know you don't know what I'm saying because you asked the question a little too soon, but if you look at the direction of my arrow, do you realize I'm going one way through resistor 2 and a different way through resistor 3 and 4? Well, it's likely the current must be going against the direction I drew the arrow in at least one of those. Probably resistor 2. Probably. But since I have to draw my arrow as a closed loop, and all the voltages have to be listed as negative, there's probably something that's going to make it one of them positive, so my equation works out. In this one, it's pretty easy to figure out the direction of the current. I guarantee you there are times when that might not be as easy to figure out. You don't have to believe me, but it's true. Okay? What I'm attempting to do, and this was I'm not trying to be flip. If we consider all of the information we have, that's it, right? We have 4 circuit elements and 1 electric potential applied in this circuit. If I want to use Kirchhoff's laws, I could use these equations to solve my circuit. You can say I gave you that it was 6 volts, and this resistor was 2, this resistor was 4, this resistor was 6, and this resistor was 8. Well, if I asked you to solve it, that would mean finding voltage and current across all these resistor elements. Do you notice right away that we generated 8 equations, potentially 8 unknowns? So if I give you some information, you should be able to figure out the other unknowns. That's what this is. Kirchhoff's laws will generate enough equations for you to be able to solve the problem using linear algebra. They'll all be linear algebra. This is linear algebra all the way across. But it represents the absolute hardest way to solve a circuit because it is an incredible amount of data and lots and lots and lots of substitutions. We'll use something that will help us make this go faster. Stepwise reduction prevents us from having to do this. But there are circuits where you can't use stepwise reduction, so this has to be a method we consider. Now for us, we'll probably never have a circuit so complicated that it'll take you more than 2 or 3 minutes to solve. And in this class, we're not going to have any that are that complicated. But if your circuit can't be broken down into series and parallel elements, you are stuck having to use Kirchhoff's laws. So let me show you what I mean by that. But can you use stepwise reduction and the rules we've just talked about to tell me what the equivalent resistance of this circuit would look like? I'm hoping that you see that there is a series of steps that will break my circuit down one step at a time, looking for parts of the circuit that match either series or parallel only. For example, I notice that the first thing I can break down is resistor 2 and 4. They are in series. So I think the first thing I can do is take my circuit and reduce it by one step. I've not changed the 9, I've not changed the 3, but the 2 and 4 are in series. And because they're in series, I have a rule for series resistors that can provide me with an equivalent resistance. And it's 6, it's not hard. That's one step in my reduction. Do I see anything here that looks like a series or a parallel? I think I do. I think I have a straight parallel element now, the 3 and the 6. I think they can be broken down into something smaller. The 9 hasn't changed. But the 3 and the 6 can be combined using my 1 over 3 plus 1 over 6 to get an equivalent resistance. And that would give me 2. We've done something similar with capacitors already, so I feel like you probably know that. But if not, you can do 1 over 3 plus 1 over 6, get common denominators, add them together and get 3/6, then invert and get 2. Good so far? I hope so, because I'm assuming you're keeping up with me. I got a couple of thumbs up. That's good. Not always worried about, some folks as I am about others. But I see now that I have 2 that are in series. Do you see it? Stepwise reduction? Not bad? Now, so we did a couple of quick practices. Put this one on the board purposefully because there is no series or parallel that can break the circuit down. You can try and attack it all you want. The problem is that there is not one resistor here that's not in direct series or direct parallel with another resistor. There would be no way to use stepwise reduction to solve this circuit. The only way you could solve this circuit would be to use Kirchhoff's rules, which, because there are 5 circuit elements, is going to generate a lot of data. And right now there are potentially 5 different currents in the circuit, 1 across each resistor, and 5 different voltage drops. There's just no way to reduce the circuit using series and parallel. So when I say to you that, yeah, we can do series and parallel, sometimes you can't. This actually has a special name. This is called a Wheatstone bridge. It is a specific kind of circuit used for very, very careful measurement of resistance. Because although you might not know it, there has to be a potential difference between here and here for current to flow over that 2 ohm resistor. So generally, you can replace one of these with a tunable resistor and use it to measure a unknown resistance by carefully tuning it until the voltage across your bridge resistor goes to 0. It's a method of utilizing a circuit like this for a purpose. Now, we're only going to deal with relatively straightforward circuits. We're not going to deal with stuff like this. Well, we can, but they're laborious. They take a long time and a lot of math, and it's a lot of just substitution. There are shortcuts, which is why I told you that whole book is made out of shortcuts to get through stuff like this. But the usefulness of this is actually pretty low. We'll do a couple of stepwise circuits just to make sure you can do them. They are not particularly interesting in that they don't do very much, but it's that practice like we do with the capacitors. Being able to reduce the circuit down means that we can study the circuit under unusual circumstances, adding some resistance or changing something about a resistor. So I do have to say one more thing though. The unit of resistance is something a little bit weird. It is a volt per amp. But volt is joule per coulomb, and amp is coulomb per second. So this is actually joule second per coulomb squared. And no, I have no idea what this is. Once you start getting into the actual units, because joule is kilogram meter squared per second squared times seconds divided by coulomb squared, it's really hard to really know what resistance is when you start looking at its complex unit. Wouldn't you agree? In there somewhere, something about conductivity. In there somewhere is about the shape and size of my actual resistor. Somewhere in there is probably something about the material in which the electric field is being presented. I don't know. That's just a lot. We call this the ohm. So the unit of resistance is the ohm. And here, just to switch it up a little bit, the symbol for an ohm is uppercase omega, or I just call it a horseshoe. But that is the unit of resistance. I think you guys are going to be very adept at this because you're good at dealing with the capacitor circuits, and these are very similar to capacitor circuits. So let's say, let's change it just a little bit from the last one so the numbers will work out nice. Let's make this 10 ohms, and this is 3 ohms, and this is 2 ohms, and this is 4 ohms. And let's make this 24 volts. These numbers will work out nice, so that's what we're going to use them. Actually, no, if I want to really make the numbers work out nice, I'd make this 36 volts. Don't count on the AP exam to give you nice numbers, but generally they don't really make it hard. They want the numbers to work out nice too. So I'm using some kind of proportion that will give us 3s, so it's not bad. Now you've already reduced the circuit, so my belief is that it doesn't take me long to convince you that the circuit has a couple of simple stages in its reduction. That's one, that's the other, and this is our final equivalent resistance. And this is 10, 3, 6, 10, 2, and then 12. Is that good for all of you? Because we already did this one just with 9 ohms. So I figured this is pretty close. Do I have to explain anything there? Because I'm hoping I can skip that part and get to the meat of this. All right, so this is our equivalent resistance. Just like with capacitance, once we get to our equivalent resistance, we can apply the voltage. But instead of how much charge there is on the resistor, we'll now have current passing through the resistor. So pretty straightforward, we're going to be using V equals IR in calculating the amount of current that passes through our resistor. So generally, it's going to be one of these two things. I have voltage and resistance, so that tells me there must be 3 amps passing through this resistor. Now I'm going to go from this resistor to a set of resistors that are in series. Kirchhoff's laws state that if there's no breaks in the circuit, the current must be the same in all circuit elements. So when I go back a step to a system in series, what do you think I apply to both resistors? Current or voltage? Gabby?
Oh, well, if it's the opposite of a capacitor, it's voltage.
It's not the opposite of a capacitor.
It's the same, so then it'd be amps.
It is amps, that's right. Because these follow Kirchhoff's laws. And Kirchhoff's laws were the same for capacitors as they are for resistors. So when I go back a step, both of these resistors must see the same current because they are in series. So 3 amps here and 3 amps here. Good so far? Now, just like with the capacitor, when you go back a step, your job now is to figure out what you are missing from what you know about with your circuit. We have the current. It's appropriate now that we figure out what the potential is across these resistors. So I'm going to use V equals IR because I have the current in each and I have the resistance of each, and I can tell me the potential across them. So there must be 30 volts across this resistor and 6 volts across this resistor. Voltage equals current times resistance, just multiplying. And it's at this point that I realize that this resistor never changes all the way back to my original circuit. So 3 amps, 30 volts. We good? All right. Unfortunately, I have to go back now here. There is a break in the current. When I go from this 2 ohm resistor, I'm going to a set that's in parallel, so I can't assume the current is the same through both. However, it's a parallel element. They must be experiencing the same change in potential. So I grab my voltage, 6 volts, and apply it to each. So when I go back to a system in parallel, you apply the voltage to all the elements that are in parallel. You now have 2 rules for stepwise reduction. They are just Kirchhoff's laws. But if you didn't write them down and you blow it on Monday when I give this quiz so that Andrew can't do well, just remember when you go back a step to a series in parallel, you apply the voltage. When you go back a step to a system in series, you apply the current. Got it down in your notes? Because now I'm back a step. 6 divided by 3, 2 amps. 6 divided by 6, 1 amp. And I'm noticing, because of Kirchhoff's laws, that 1 amp plus 2 amps equals 3 amps. There was 3 amps here before. Follow? Just like 30 volts and 6 volts was the 36 volts that was here before. Lots of ways to check your work between steps. All right, well, this is 6 volts. This is 2 amps. But now I have to go back here. I'm going from a resistor by itself to a resistor in series. So what do I take with me, current or voltage? Current. So 1 amp, 1 amp. To find the voltage, 2 times 1, 2 volts. 4 times 1, 4 volts. There was 6 volts there before. 4 plus 2 equals 6. Nice and straightforward. We have essentially solved the circuit, except for one thing. When we had capacitor circuits, there was always a discussion of how much energy was stored in the circuits, but resistors don't store energy. They dissipate power. They consume power. They use energy. Power is the rate at which work is done. If you don't remember that from mechanics or from AP1, let me reintroduce it for you. Power is the rate at which work is done. It is work over time, which means it is joules per second, also known as a watt. A 100-watt light bulb is consuming 100 joules of energy each second. and hopefully producing 100 watts of light. It is not. Generally, it's producing way more heat than it actually is light, which is why you should use LEDs and not incandescent bulbs, which can produce as much light with very little heat. That's why we should switch to LEDs, because a 100-watt equivalent means it doesn't use 100 watts. Generally, about 12 watts, but produces the light of a 100-watt light bulb. It just doesn't produce as much heat. It's kind of crazy. Most of the lights in your house are doing as much to increase the temperature of the air as they are to light up your house. And so you spend more energy getting it cold in there again. So there's a good reason to switch to LEDs. It saves power twice, right? Once on cooling your home, we live in Florida, and once producing light. So, but calculating power in an electrical circuit is the product of the voltage and the current. Unlike energy stored, where you have to do calculus that we didn't do to figure out the stored energy, this is a definition. Power is voltage times current. And using Ohm's law, there are other ways to write it. So just be aware. There's always usually an easier way. But I'm getting 102 watts of power, right? 3 times 36. Is that 102? 3 times 6 is 12. 3 times 3 is 9 plus 1 is 10. What's that? You're right, 108. God, why did I say 3 times 6 is 12? Because Mr. Shelton. Yeah, 108 watts. It should be capital W, yes. It's a name. Now, you should be able to go through here and figure out all the individual powers. Like 4 times 1 is 4 watts here. 2 times 1 is 2 watts here. 3 times 30 is 90 watts here. And 2 times 6 is 12 watts here. 12, 4, 2, and 90. 90 and 12, 102. 102 and 2, 104. 104 plus 4, 108 watts. An equivalent resistance has to consume the same amount of power as the individual resistors that make up your system. So the same was true with capacitors. The equivalent capacitor stored the same amount of energy as our system of capacitors stored individually. Same kind of check of our work, though. Now, you can probably imagine why I'm going to say this, but I don't see that we have to do 100 of these to get this down. You notice that this is very similar to what you've done before. On the other hand, if you're good at this, great, prove it. But if you're bad at this, you need practice. Now, I can provide an infinite amount of practice, but I probably won't. I will probably put a single practice with 4 or 5 examples up on Canvas for you guys to try them out, be able to reduce a circuit, because this is not what our unit is about. Although I think you have to be able to do this, our unit wants to be about more than just this. This is what we would do in something like honors physics. That's where they would do this, regular physics. Maybe not with 4 resistors. That might be a lot for regular physics, but not so much for honors physics. But I want you to practice. I'm going to post some practice so you can give it a try. And try the hard one first. If you can do the hard one, don't do the easy ones. But if you can't do the hard one, do the easy ones. Yes?